All right. So this is going to be kind of a grab bag talk that's going to talk about three different things: um, the shapes, masses, densities, and then also a bit of future work here. So the motivation for understanding what the densities of the small satellites is just understanding this formation process. So this is one of Edine's simulations that she showed this morning. Um, but the key factor there is just that little um, spray going out the side there that forms this debris disk that eventually forms the small satellites. Um, and the only probe that we have, other than trying to look in, the bulk density of Pluto and Charon, is looking at what are the compositions of the small satellites. So Brian after me is going to talk about the composition of their surfaces. The other way to do that is to go after their density. And the trick with the density is we can't entirely constrain this from just New Horizons data, but we can use the New Horizons data maximally to do the constraint and then add it in as much as we can. So we need to have both the shape models that are determined from what small amount of imagery we got during the Pluto flyby, um, as well as photometry before and afterwards, and then combine that with dynamical models of the system to determine what the masses are. So uh, for doing the shape models of the objects, we have a very limited amount of data for these. We have like 6 resolved epochs for Styx. We've got 5 for Hydra. We've got 2 for Kerberos and 1 for Styx. It's not a lot. But what we do have a lot of is this approach photometry from New Horizons, because we were looking at them as they were coming in. Now it's only at a single phase angle, but it's fairly dense. So we can take the OpenGL-based shape modeling software that I've been using to do the shape model do previously, and throw it at a GPU and do a whole lot of rendering on it, and make sure that any shapes we get are consistent with both this approach light curve as well as the resolved imagery, and just do a combined solution that way. And it turned out to work really well, actually. And then this sort of combined process, at the moment for this, I was just doing it with the New Horizons data, but we can go back and start applying this to the historical photometry as well as photometry in the future, so we can start to see the evolution of the stuff. So just to start with Nix, the one that we have the most amount of data for, we got closer to Nix than we did Hydra, and both Nix and Hydra have multiple observations because they were discovered before New Horizons wrote the observations sequence. So most of the images of Nix are show an elongated object, except for I kind of threw in the only one that shows it round. This is actually the first really resolved one we got down, so we thought Nix was round for about a day. And then we got all these other ones that shows elongated, and you can see in the approach light curve, it is very elongated. And this was really nice because I kind of had a shape model already for it that was pretty good, and I threw it into light curve and it fit almost immediately. So that was nice verification. One thing for this is we are getting albedos for Nix and Hydra that are very similar to Charon. It's not exactly the same, and that might be down to peculiarities with the overfitting the Hapke model there. But generally speaking, the albedo is pretty similar for Nix and Hydra to Charon. And then the best fit size is there for Nix. You can see it's fairly elongated, but with a volume equal to a sphere of 37. And then for Hydra, So for Hydra, it's a faster rotator, but we only saw one hemisphere of it, or one half of it. It's not a sphere. Um, so we didn't have the best constraint on its volume just from the images, but we did have this really nice light curve that you can see it's got this extremely complex shape to it that would baffle you if you didn't have an image, and then we have images and it's still baffling. Um, but basically, it kind of looks like a shoe. Um, so it's kind of triangular in shape. These little holes on the side there are just down to the fact that the sun is coming in from this direction, so that's just shadows there. So there is material there, it's just in shadow. And you can see that over this one here, there's a little bit of valley there, but again, that's shadowing for the most part. Um, so it's a flatter shape than overall than Nyx, but slightly lower volume, and that'll be important in a second here. Kerberos. So we only have two images for Kerberos. This is one of the two. But we do have a really nice light curve for it. And this took a bit of filtering because there are so many background stars, so I had to really work to filter out probably about 10% of the photometric observations were just contaminated with starlight. But when you filter it out, you get this really nice light curve out of it. And then so using the two resolved images plus the light curve, and then assuming that it's a triaxial ellipsoid shape. You can get some constraints on the size, so that's the best fit size with a volume diameter of 9.5. And then you get this sort of map for the poles where the lighter the color, the better the fit. So, you can't say exactly where the pole is of Kerberos, but you can constrain it to these. And that's sort of at the time of encounter. Now, we expect that all of these are probably experiencing some sort of pole variation over time. It's spinning fast enough that it's not quite what Mark Showalter and Doug Hamilton had said before, where it's like completely chaotic. It's probably chaotic over long time scales, but processing and annuating over shorter time scales. But we've had enough time since flyby now that we start to get photometry of these things, we should be able to start to see differences, and that can actually constrain our pole. So that's really encouraging that we have this initial map and then we can try and get better from there. The other trick with Kerberos is it a contact binary? Because it kind of looks like in this image, and it looks even more so in Todd's deconvolution, which I was going back and forth whether I believe it or not. But so that's what the actual data looks like. This is just subtracting a triaxial ellipsoid, and you get sort of this high, low, high. And this was the best fit I was able to get with a contact binary, just using the Arikoff model, but just two triaxial ellipsoids, and you get sort of different looking residuals. It's a bit better fit, but it might just be a case where you're overfitting because you've got more parameters. But it is true that if you have the contact binary solution, it pretty much removes this second pole option. So it really strongly says that the pole's over here. So that's further motivation for trying to get more of this photometry in the future. If you can exclude this pole, then that's sort of saying that, oh, it's not this contact binary solution. But if you can't exclude it, or if it's sort of moving towards the same, then that's stronger evidence that it's a contact binary. But just from the light curve alone, it doesn't seem to be that much of a better fit. And then finally Styx, the one that we have the least amount of data for, but as you saw from Scott's talk, is the single most interesting one of these. And we have one resolved image of it. I mean, there's not a lot of shape information there, but it's there. And it wasn't too high amplitude of a light curve, but is there, and we're able to do something with it. So we can kind of constrain the shape down to about 7 kilometers total volume. And then there's these 4 different pole solutions that's just completely degenerate between. But again, longer term evolution, we can do better. Probably not with HST because it's really ratty to get any photometry for this object with HST. So speaking of HST, in order to get the masses of the objects, it's this combined solution of all the data we've got, which is both the HST astrometry, which goes back to 2007, or 2006 actually, because there's some pre-coveries. And that goes through 2019. So 2006 to 2019. And then we have the New Horizons astrometry, which gets up to really high precision at the time of flyby, but it's all in 2015. So you have this hyper precision around the time of encounter, and then lower precision before and after. So you have to combine those 2 data sets together in a single fit. These are the residuals that I got for mine. So it's chi-squared in log space. So, and then you can see the different objects, and we can we don't have sticks out to here because this was using WIFPIC 2 and ACS, and it couldn't detect sticks. It did actually manage to get a bunch of pre-coveries of Kerberos, which was nice, but sticks wasn't detectable until the WIFC 3 era. And even then, on the New Horizons approach, it wasn't until we got very close in that we actually had sticks. So sticks is definitely the least constrained of any of these satellites, and that's very important for stability. So this is just a corner plot of the 4 mass constraints that we got from that survey. And as you can see, we have strong constraints for Nix and Hydra, with Hydra being slightly more massive than Nix, but them both having densities above 1 based on the volumes from earlier. And for formation, that's really important because you can't just make these out of pure ice. Even if they were completely solid frozen ice, you can't make densities of 1.2, 1.1. So they have to have some rocky component to them. And because they're probably have large amounts of porosity to them, they probably have significant amounts of rock. We were only really able to get sort of rough constraints for Styx and Kerberos, and improving that is just only going to take more observations over time as we get longer arcs. But it's probably going to be easier to constrain Kerberos than it is Styx, just because Kerberos is between the 2 larger ones. So you'll be able to get an upper limit, but also a lower limit, because eventually you'll start to see the effects of Kerberos onto Nix. So so on this plot, so you got porosity versus ice fraction, and then with the estimated rock ice fraction for Charon and Pluto. So you can see, if we just assume that it's the same rock ice ratio, then we're talking about a bulk porosity of 20%, which is, pretty good, but the porosity could easily be much higher than that, and then that would imply even more rock fraction to the object. So probably these objects are fairly porous, but they're also very rocky, and that's, I think, probably the most important thing to come out of this talk. If you just remember the fact that Nix and Hydra are fundamentally rock ice mixtures. And then finally, I was able to get some HST time last year. 3 orbits. I maybe should have asked for more, because the more the better, but 3 was enough, and all 3 worked. So these are the most recent images of Pluto taken with HST. You can see this one was a, a bit low elevation, so we got Starlinked right across there. But that's Pluto, Charon in the center there. So those are the full frames. And the other thing to note here is if you've seen historical images of Pluto taken with HST, there's always tons of stars around. And we're at the point now where I actually had to take full frames for these just to make sure that I had enough stars around them. So Pluto's really moved out of the galactic plane quite a bit. But the motivation here, so these are uncertainties based on the 2023 orbit solution for Styx, Nix, Kerberos, and Hydra. And so you see the, uncertainties don't really increase for Nix and Hydra. It's going to take a while to really get there. But for Styx, they're really climbing up because it's the least well-constrained of the objects. And then the black line there is the resolution you get from HST, and it's a wiggly line just because of the orbit of the Earth. And then this is in kilometers. So you get a little bit further and closer, and that's why it's a wiggly line. But then there's a secular trend where it gets worse because Pluto's getting away from the sun. But you see, we've hit that crossover point now where we should be able to make a better constraint with Styx. And as time goes on, the more constraints we can get on Styx, the more we'll be able to actually improve that orbit. So that's my summary. Those are all roughly to scale with each other. So it shows you how much worse our resolution was on Kerberos than the other guys. But the take home is definitely these are rock ice mixture objects on their interiors at least. And we need more data to improve their orbits. And this is going to be a continuous process for the next few decades to try and really nail down that orbit for Styx. So thank you very much.
Hi, Simon. I'm giving the next talk, so I'm gonna ask a cliffhanger question. You found that Nix has a larger equivalent diameter and is a higher albedo than Hydra.
Mm-hmm.
That is fascinating.
Yeah, and also the paper I did with Will years ago, the general trend of dust in the system is inwards. So it could be that Nix is somewhat contaminated with Hydra dust if Hydra is much darker. But I didn't see anything consistent with Styx or Kerberos being particularly dark compared to the other ones.
Casey?
Fascinating work, Simon. Thank you. I'm struggling with a physical picture. We know that the small moons are very icy, are very shiny. You've just told us they have.
Well, they're not that shiny. That's kind of the point. They're the same shininess as Charon.
Well, that's where kind of was going. We know from what you've just said is they have a lot of rock in them. We don't necessarily expect when they reaccrete after a collision that they have. What is the process that you would get a rock in the center versus on the surface, or should this be uniformly mixed ice and rock?
Yeah, that's my assumption. Is it would be uniform. Yeah.
And does that fit with all the other observations that we know of?
Well, that's for Brian to talk about next.
And also to think about Howell's paper.
Yeah.
Okay.
Yeah. I think we had some slightly erroneous sizes in Howell's paper, and that gave high albedos. The albedos I'm getting for these are consistent with Charon.
What kind of numbers? So 0.3 or 0.4?
0.3, yeah.
Thank you.
Yeah, but I mean these are fit albedos, and I can't fit with 0.7.
Hal may say something later. Let me ask you a question. Since you were talking about a contact binary, but what about Hydra? That very unusual shape.
So it's not a contact binary, but it is lumpy.
Yes.
And so that probably says something very important about formation, that this wasn't a fast accretion of it. It was probably a slow coming together of bodies that were co-orbital, and then they had like a centimeter per second or something accretion.
Okay, now I guess I would have asked a question about whether we can, how much actual dark rock we can make consistent with these albedos, but I guess that'll be the next talk. But
All right. Well, thank you very much.
all right.